I thank each one of you for watching my videos and encouraging me. Please like my videos and share them with your friends and colleagues. Please subscribe my channel if you have not already subscribed. Thank you. We now discuss the solutions of the previous year questions from the section analysis that have appeared in the CSIR National Eligibility Test. In this video, we discuss 3 questions, question numbers 15 to 17. These questions are suitable for all these examinations. Right. This question has appeared in 2019 June and it is related to countable, uncountable sets. The given question is, which of the following sets is uncountable? We are given 4 options. Option 1, the set of all those x belongs to R such that log x is equal to p by q for some pq belongs to n. Option 2, the set of all x belongs to R such that cos x to the power of n plus sin x to the power of n is equal to 1 for some n belongs to n. Option 3, set of all those x belongs to R such that x is equal to log of p by q for some pq belongs to n. Option 4, the set of all those x belongs to R such that cos x is equal to p by q for some pq belongs to n. Right. We now discuss the solution of the problem in detail. Let us take the option 1. Now, in the option 1, it is given the set of all x belongs to R such that log x is equal to p by q for some pq belongs to n. That means log x. Log x is p by q, then x will be e power p by q. Therefore, it will be the set of all e power p by q, pq belongs to n. When pq belongs to n, what will be p by q? It is a positive rational number. Positive rational number. So, this is the set of all e power r, where r is p by q, where p by q is a positive rational number. Therefore, r belongs to q plus. So, for each r belongs to q plus, we have e power r and conversely. So, this how many of these things will be there? As many as there are in q plus. So, that means note that q plus is countable. Therefore, the given set is also countable. Since why q plus is countable? Since q plus is an infinite subset of q. What is q? Q is countable. An infinite subset of a countable set is again countable. Therefore, q plus is countable. Therefore, the given set is countable. But we have to find out that set which is uncountable. Therefore, option 1 is not true. Agreed. Right. We move on to option 2. Set of all x belongs to R, cos x whole power n plus sin x whole power n is equal to 1 for some n belongs to n. That some n is equal to 2. So, you substitute cos x, that means cos square x plus sin square x is equal to 1 for all x belongs to R. So, this will be, we have cos x to the power of n plus sin x to the power of n is equal to 1 for n is equal to 2, and this is true for all x belongs to R. Therefore, this set is equivalent to R, where R is uncountable. Its cardinality is C. Therefore, this given set is uncountable. And we have to find out that set which is uncountable, and we have found. Therefore, option 2 is true. Right. We move on to the next slide. Right. We have here options 3 and options 4. Let us first of all take option 3. X belongs to R such that X is equal to log of P by Q for some PQ belongs to N. That means it is a set of all X is equal to log of P by Q, PQ belongs to N. That means it is the set of all log R, where R is P by Q, where P by Q is a positive rational number. So that means log R, where R is P by Q, where P by Q is a positive rational number, therefore R belongs to Q plus. So a set of all log R belongs to Q plus, is equivalent to Q plus, and Q plus is uncountable, is countable, is a countable set. Sorry, it is countable set. Therefore, option 3 is not true. We have to find out that set which is uncountable, but it turns out to be countable. Therefore, it's not true. Option 4. X belongs to R such that cos X is equal to P by Q for some PQ belongs to R. PQ belongs to N, set of natural numbers, is equal to set of all X belongs to R, cos X is equal to R, where R is P by Q, where P by Q is a positive rational number. So R belongs to Q plus. So this is we have to find out all those X belongs to R. Therefore, cos X is equal to R means X will be cos inverse R. So cos inverse R belongs to Q plus. And what is the domain of cos inverse R? The domain of the cos inverse R, the closed interval 0 to 1. So in that we have to get all those R belongs to Q plus. Therefore, the closed interval 0 to 1 intersection with Q plus. And obviously, it's an infinite subset of Q plus, and it is countable. It is countable. So, we have to find out uncountable set. Therefore, the option 4 is not true. Summarizing all the options, our answer is option 2. That is the detailed discussion of the solution of this problem. Right. We move on to the next question. Right. It is the question that appeared in 2013 December and under section C, carrying 4.75 marks. It's again based on the concepts of countable and uncountable sets. Which of the following subsets of R square are uncountable? We are given 4 options. Option 1. The set of all ordered pairs A, B belongs to R square, where A less than or equal to B. Option 2. The set of all ordered pairs A, B belongs to R such that A plus B belongs to Q. Option 3. The set of all AB belongs to A, B. All ordered pairs A, B belongs to R square such that the product AB is equal to belongs to Z, the set of integers. Option 4. The set of all ordered pairs A, B belongs to R square, where A and B are rational numbers. Agreed. Let's now discuss the solution of the problem in detail. We have R square, is a set of all ordered pairs X, Y, X belongs to R, Y belongs to R. Agreed. Consider option 1. The set of all ordered pairs A, B belongs to R square such that A less than or equal to B. So let this set be capital A. Now consider B. B is the set of all ordered pairs 0, X belongs to R square such that 0 less than or equal to X or X greater than or equal to 0. So what is this? It is the set of all points on positive x-axis in R square including 0, 0. It is the set of all points on the positive x-axis in R square union the 0. Right. Note that B is a subset of A. Agreed. Correct. And B is the set of all 0, X belongs to R square, 0 less than or equal to X is equivalent to R plus that is positive real numbers, union one more point. Union one more point. So what is this one? This is the interval 0 to infinity where it is closed at 0 end. And this semi-closed interval 0 to infinity is an uncountable set. Yes. Yes. All intervals are uncountable. Right. All intervals are uncountable. Right. Therefore, A is an uncountable set because B is a subset of A and B is uncountable. B is an uncountable subset of A. Then A will be uncountable. Option 1 is true. Right. We have to find out that set which is uncountable. So, option 1 is true. Option 2. All ordered pairs A, B belongs to R square such that A plus B belongs to Q. Call this set as A. Right. Let consider the set B consisting of all ordered pairs X, minus X, where X is irrational. Where X is irrational. Irrational means it is irrational. Right. Now B is the set of all ordered pairs X, minus X belongs to R square because every irrational number is a real number. Belongs to R square such that their sum is 0 where 0 is a rational number. So obviously B is a subset of A. B is a subset of A. Note that B, what we have considered here, is equivalent to how many elements will be there? As many as there are the irrational numbers. So B is equivalent to set of irrational numbers and B is uncountable. Why? Because the set of irrational numbers is uncountable. R minus Q is uncountable. So what is now B? B is an uncountable subset of A. Therefore, A is also uncountable. Agreed. B is a subset of A and B is uncountable. Therefore, A is uncountable. Option 2 is true. We have to find out uncountable sets. Right. We go to the option 3. The set of all ordered pairs A, B belongs to R square such that the product AB is equal to Z. Let's call this as the set A. Consider the set B is equal to the set of all ordered pairs X, 1 by X where X belongs to R star. R star means non-zero real numbers. And now B, set of all ordered pairs X, 1 by X belongs to R square. And the product X into 1 by X is 1. 1 is a integer. And good. So that means B is a subset of A. B is a subset of A. Note that B is the set of all X, 1 by X. X belongs to R star. How many elements will be there in B? As many as there are in R star. Because for each X belongs to R star, we get an ordered pair and conversely. So B is equivalent to R star and B is uncountable. Why? Because R star is uncountable, right? And B is an uncountable subset of A. Therefore, A is uncountable. A is uncountable because B is contained in A and B is uncountable. So option 3 is also true. Go to the option 4. Set of all ordered pairs A, B belongs to R square where A and B are both rational numbers. Now the set of all ordered pairs A, B belongs to R square where A and B both are rational numbers. It is same as the set of all ordered pairs A, B where AB belongs to Q, because A, B belongs to A, B are rational numbers. So how many these? These are as many as there are Q cross Q. These are as many as there are in Q cross Q. What is Q? Q is countable. Q is countable. Its cardinality is LF naught. So Q cross Q will have the cardinality LF naught cross LF naught, and LF naught cross LF naught is LF naught. That is, Q cross Q is countable. Now, is countable because Q cross Q is countable. But we want uncountable sets. Therefore, option 4 is not true. Summarizing all the options, we get the answer as options 1, 2 and 3. That is the detailed discussion of the given question. Let's move to the last question in this video. The given question is from 2018 December question paper. It's again from part C, carrying 4.75 marks on countable and uncountable sets. All the 3 questions what we have seen, we have taken are based on concepts of countable and uncountable sets. The given question is, let S be an infinite set. Which of the following statements are true? We are given 4 options. Option 1, if there is an injection means 1, 1, from S to N is set of natural numbers, then S is countable. Option 2, if there is a surjection means onto from S to N, then S is countable. Option 3, if there is an injection from N to S, it is reversed, then S is countable. Option 4, if there is a surjection from N to S, then S is countable. Good question. Now let's discuss the solution of the problem in detail. We are given S is an infinite set. Remember, S is an infinite set. Take the option 1. If there is an injection from S to N, then S is countable. We have, let us say, a function f, S to N, an injection. Injection means f is 1, 1. When f is 1, 1, the cardinality of S is less than or equal to the cardinality of N. That is, the cardinality of S is less than or equal to N. Cardinality of N is LF naught. So cardinality of S is less than or equal to LF naught, and S is infinite. What is the possibility? So the cardinality of S is equal to LF naught because S is an infinite set. So that means cardinality of S is LF naught, means S is countable. Therefore, option 1 is true. Let us take the option 2. If there is a surjection from S to N, then S is countable. We have a function g from S to N, a surjection means g is onto. Therefore, order of S, that the cardinality of S greater than or equal to cardinality of N, because g is onto. So that means order of S is greater than or equal to order of N. The cardinality of N means LF naught. So cardinality of S is greater than or equal to LF naught, then 2 cases arise. If cardinality of S is equal to LF naught, because greater than or equal to, therefore we are considering equality, then S is countable. The second possibility is the cardinality of S is greater than LF naught. So after LF naught, what will be there? It is uncountable. So S is uncountable. So we have 2 possibilities. But is it necessarily onto? No, not necessarily on. Necessarily countable. Is S is countable? Is not necessarily countable. If there is a surjection from S to N, then S is not necessarily countable. It is not necessarily countable. Therefore, option 2 is not true. We move to the next slide. Remember, S is an infinite set. Consider option 3. If there is an injection from N to S, then S is countable. We have a function f from N to S an injection, means F is 1 to 1. When F is 1 to 1, the cardinality of N must be less than or equal to cardinality of S. That means reverse this, cardinality of S greater than or equal to cardinality of N, that is LF naught. So what will be cardinality of S greater than or equal to LF naught? Two cases arises. If equal to, if order of S is LF naught, then S is countable. If order of the cardinality of S is greater than LF naught, then S is uncountable. Therefore, we cannot infer, we cannot conclude that S is countable. It is not necessarily countable. If there is a surjection from N to S, there is a print mistake here, not from S to N, N to S, N to S, N to S, then S is not necessarily countable. Option 3 is not true. In this, here it is a print mistake. It should be N to S. Option 4. If there is a surjection from N to S, then S is countable. We have G from N to S, a surjection, G is on to. Therefore, order of N, order means the cardinality of N greater than or equal to cardinality of S. That means, reverse this, cardinality of S is less than or equal to cardinality of N, that is LF naught. This means cardinality of S must be equal to LF naught because S is infinite. S is infinite. That means S is a countable set. Therefore, option 4 is true. Combining, summarizing all the options, the answer to this question, options 1 and 4. That is the detailed discussion of the solution of the given problem. And in this video, I have discussed 3 questions based on a single concept, countable and uncountable sets. And some of them are from part C. And all of them are easy. I am sure that you have understood the solutions of all these 3 problems. Thank you for watching the video now. Please like my videos and share them with your friends and colleagues. Please subscribe my channel if you have not already subscribed. We hope to meet you once again in another episode of learning. Enjoy learning mathematics. I wish you all the best. Thank you.